Now it's time to move on to the feed-forward network. The purpose of the feed-forward network is to introduce non-linearity into the model. We don't even have to think about something as complex as the transformer architecture to understand this concept. What we can really just focus on is linear regression versus a neural network. Linear regression can fit a model to a straight line or a linear line. Because the base of linear regression is y equals mx plus b, where b is the bias, m is the weight, and x is the input feature. Now, this is if our input vector was a vector of 1 with a single x. In our instance, where we have a vector of 8, our linear regression function would look more like this. For an input vector that had 8 features, 8 values, like ours, our y equals mx plus b would look something like this. We have our bias, and then we have our m1 times x1 plus m2 times x2 plus m3 times x3, all the way to m8 times x8. Now, we're not going to cover bias here because it's a little out of scope, but it's just worth noting that for every weight vector, there actually is a trained bias depicted as the 0th weight times x0, where x0 for all of our input vectors is actually a static value of 1 to ensure that we account for bias. But again, that's out of scope for now. Now, another way we can rewrite this equation in a manner that we've been discussing for the last 45 minutes or so is as the dot product between our weight vector and our input. Because recall that the dot product between two vectors equals a scalar. Now, when discussing linear versus nonlinear models, linear models, or the dot product, can only ever predict something on a linear or straight line. Again, ignoring the bias for now. If we were to add a second x value, which we can either call z or x1 and x0, then we can predict the y value based off of that additional context. Understand, though, it will always be predicting on that linear line or linear plane, or some linear representation in higher dimensions. Now, to allow a model to learn complex patterns and functions from data that can't be diluted down to a linear line or plane, you have to bring in nonlinearity. How this is done is that at each neuron, you compute the dot product, and then you run the resulting y through a nonlinear function. Whether that be the ReLU function, which still outputs the linear value of anything above 0, but anything negative or below 0, it just outputs 0. The sigmoid, which takes in an x, and as x approaches positive infinity, the resulting output of the sigmoid function gets closer to 1. And as the input value approaches negative infinity, the sigmoid output gets closer to 0. And if the input is 0, then the sigmoid function just outputs 0.5. Tan-H, which is similar to the sigmoid function, except it's between -1 and 1. The GeLU, which is similar to the ReLU, except that it doesn't have as harsh of a drop to 0. It has a softer landing and permits some negative values based off of the values distribution. Within transformers, the most common activation function at each neuron is the GeLU. It's been shown to outperform the ReLU function. There are other activation functions that are out of scope and I won't touch on, but this is a topic of ongoing research for better improvement in future models. A good way to think about nonlinear models is it provides the space for models to learn new parameters, parameters that it wasn't given. I'm going to show an example of that here so that we have a much better concept of how the feed-forward network differs from just the simple attention layer. My example will be doing a side-by-side of basic linear regression and a basic neural network, but the concept, the takeaways, are still the same. So let's assume we're predicting the price of a house and we have the following input. Our input vector has 6 features depicting the square footage of the house, the distance from a local elementary school, the number of bedrooms, the crime rate in the area, whether or not there's a local pro sports team, and if there's a community park in the vicinity. We could train a respective weight vector where when we compute the dot product, we can get a predicted house price. And this is well and good, and it can be relatively accurate across the 6 dimensions, but the issue is our linear model can only ever deal with these rudimentary features. It doesn't allow the space for us to abstract a higher meaning from the relationship between these features. For comparison, we're going to show how this works with the neural network. Okay, so our network has 2 neurons, both of which are just a weight vector of the same size as their input vector. So similar to the linear regression above, we will just compute the dot product of each neuron initially. Recognize that these two weight matrices are not equal. They're different weight matrices. So after we compute the dot product and we get y0 and y1, both of these linear outputs will be fed to an activation function. This activation function can be one of these or other nonlinear transformations. So sigmoid would put the output between 0 and 1 based off of if it's between negative or positive infinity. Tanh would put it between negative 1 and 1. ReLU, GeLU, all are different nonlinear transformations to our linear output. Each of these neurons then outputs a scalar value. We'll put S1 and S2, which are the outputs from our nonlinear transformation of our original y values. For the sake of simplicity, let's just assume that these then route to the final output layer, where the final output layer has a weight vector. The output from our prior neurons is now treated as the input for the next neuron. So the next neuron in our final output layer must have a weight vector that matches the number of inputs coming in. Now, we didn't touch on bias, but we will have an M0 because we have to account for bias, and we're going to add a 1 there. Again, I don't want to focus on that for now. We compute the dot product, which results in a linear output, which is ran through an activation nonlinear function, which results in our final output. Now, let me clean this up a little bit. So this can be broken up as our original input, a hidden layer, and our output layer. Now what we can see is our eventual output, our eventual prediction, was the result of this abstract feature vector dotted with the output weights with a final nonlinear transformation. While our original linear regression was able to make a prediction based off of the rudimentary features such as, distance from school, low crime rate, what our neural network now allows is for this first layer to result in the relationship between our parameters. So we can now imagine that the output from our first layer results in two new, more complex features. Imagine that for x1, these weights were trained and tuned to understand the relationship between distance from school and low crime rate, resulting in a new feature that highlights how walkable an area is. Similarly, this dot product's activation might have learned how entertaining an area is based off of if there's a community park and a local pro sports team to cheer for. Now, this is a trivial example, but the concept is that if you allow the model to learn the nonlinear relationships between the distance from a school and the crime rate to understand the walkability of the surrounding neighborhood, that is a better predictor of price than the more rudimentary features. Now, conceptually, that makes sense, right? But let's go back to the question. Why do we need the activation layer? Why do we need the nonlinearity? What would the result be if we got rid of the nonlinear function of the neuron? The issue here is that if you get rid of the activation function at each neuron and instead make each neuron just a simple dot product, then if we carry out the math, it really is just one long, complex dot product that isn't creating the space for you to learn any complex relationships. Let me show you here. Let's assume that this is the resulting dot product from the first neuron, and this is the resulting dot product from the second neuron. This means that this is reflective of our new x1, and this is reflective of our new x2. If we now compute the dot product of our output layer, ignoring the bias for now, that would result in x1 times m1 plus x2 times m2. Now, if we distribute out m1 and m2 respectively, we get the following equation. When we view it like this, we can see that this really is just a very long, drawn-out version of y equals mx plus b. Therefore, if you don't add nonlinear activation functions to each neuron, then adding additional neurons really isn't increasing the accuracy or effectiveness of your model. There's no new knowledge or relations. You're just simply redundantly using your same rudimentary features more than once in the same y equals mx plus b equation. Now, let's relate this back to our main topic. If we look at what we did in the attention layer, there really was no nonlinearity. We took the dot product of a lot of vectors, and while we did do the softmax function of our attention matrix, which is technically nonlinear, and we did normalize our final output, Neither of these really adjusted the relationship between the features. They merely represented the same relationship in a different, normalized, stable way. So while the attention layer allows us to represent our original input in a more relevant contextual way, our feed forward network allows us to add nonlinearity so that we can understand more complex relationships between our new attentive features. And by features, I'm just referring to the different dimensions. With that background, it's finally time to dive into the feed forward network.